Ladies and gentlemen, our next speaker is the distinguished designer for Sitara MPU product lines, bringing over 10 years of embedded Linux experience to the stage. Devarsh Thakur is not just any engineer, he is a visionary who understands the pivotal role that graphics, display, and multimedia play in defining the user experience of any product. Today, he will unravel the mysteries of accelerators integrated into TI SoCs, guiding our technologists and engineering teams on how to leverage these accelerators for graphics, multimedia, and display use cases. Without further ado, let's welcome to the stage Devarsh Thakur. Thank you.
Very good afternoon to all of you. Hope you all are having a great time enjoying all these informative sessions and innovative demos that we have prepared. So a little change in topic. It's not just about user-rich HMI experience. I'll be covering TI's display, graphics, and multimedia offering, as I believe it can be used anywhere, be it automotive, industrial, or personal appliances. So a little bit about myself. I'm an embedded software engineer with some experience, and my expertise is mainly on Linux kernel and multimedia side. And so when I joined this industry 10 years back, so my manager used to say that, hey Devarsh, this is one feature, you have to write a driver, and I would ask like, what should I test? They would say that just test the performance, it should reach good performance and it should be okay. So my goal only, not just from the processing perspective, you can say that we are scaling on the GPU part, display part, DDR bandwidth part, and the video accelerators part too. So if you see like entry level, we have this AM62L SoC which is coming soon, which has a single, also you can connect, or DSI, and it has a software video codec that you can use. So this device you can use for medical appliances or entry level HMI devices like this. Okay, just a second. Yeah, and going little higher, you have AM62 SoC. This has a quad-core A53 processor, higher DDR bandwidth, and it has a video codec also. And along with that, a JPEG encoder is also there. So this you can use for applications such as camera mirroring systems and video telephony use cases, and let's say entry-level HMI, all that stuff. I got some let's say examples for that. So in the car, you have this side view mirrors. Nowadays, it is getting replaced with this. So this device, you can use it as a camera mirroring system also, where you can connect a camera and it displays you the feed. So yeah, and how many of you in your cars, you are having a front camera for recording, like in case accident happens or something? Okay, so similar to aeroplanes, we have nowadays in car this black box video camera recording applications. So this codec can be utilized there also, like you can record live feed of when your vehicle is moving and there is a crash happening and everything. So you have a recorded, encoded feed that you can process, and that will help with legal stuff also. And JPEG you can use for selfies, and like in the car, if you have to take some pictures, runtime pictures of cameras and coming from camera feed and all that you can do. Moving little higher, we have AM62 SoC, and that's where the game changes, like in terms of higher HMI, like because all these devices now we have a GPU also, and we have multiple displays. So this has a GPU with almost like 8 G-flops, and it has a dual display support. So nowadays in the automotive side, you see like we have multiple displays that need to be supported, right? So these type of solutions can help there. And it has if you want to have duplicated displays, then we have a clone mode support in Oldie, where you can duplicate your video across multiple monitors. If you go even higher, then we have this AM62P SoC, which is a brand new SoC, and it can support up to 3 displays. So here you have a GPU, you have multiple displays which almost go like wide 4K. We have a good DDR bandwidth, and we have a even stronger hardware video codec. So this device you can use not just for HMI, you can use for automotive display cluster solutions, or even entry-level IVI, and so many stuff like video telephony, etc. We'll see that in further sites as well. And if you go even higher, then we have AM68 and AM69 SoCs, which are A72 core based, like this. This one is dual core A72, this one is 8 core A72, and we have a good GPU here also. And here you have like up to 4 displays, and this guy supports single instance of a video codec. Here we have 2 instances of video codec. So this is like you can do automotive, digital clusters, in-vehicle infotainment, integrated cockpit with multiple displays, and so many stuff you can do with this. So I said in-vehicle infotainment, so you can see like there's a rear view display that you can see there are multiple display requirement here. So you can power it on from a single SoC and have multiple displays rendered with infotainment feed. One more thing with all these high-end SoCs is like there are AI engines as well. There is a GPU, so you can use it for high-end use cases like auto valet parking and surround view systems. So when I say surround view, this is one example. Like we are creating a the surround view of the vehicle we are driving, and we want to see it from the rear view, how it looks. So this, you have a codec, you have a GPU, you have cameras. So we capture feed from multiple cameras. If there are multiple ECUs in car, then you can stream it over Ethernet, the encoded output of those cameras. You can stitch it together, and you can display it and create a surround view stream. So even all these complex use cases, ADAS-based use cases, you can do with all these processors and many more use cases. So to back this hardware story, we have a very robust software, which is, as I mentioned, power efficient, unified SDK, 100% software scalability is there. So this is one example of the SDK experience that you get like when you download a Wikimage from our portal. So you can see we are having out-of-box examples for industrial HMI, live camera benchmarks, CPU benchmarks, and GPU performance and browsing. And you can see we are displaying the GPU load, CPU, and DDR bandwidth. And all this is Qt based and GPU accelerated. So it's a very cool platform to start your application benchmarking. So as you can see, you can go to the portal and you can download Wikimages, and we have Debian flavors also. We have JLaws flavors in case you are interested in virtualization testing. And we have support over RT Linux and Android. And one more thing is, like this is all for the A cores, right? But what about the MCU cores? What if you want to access multimedia peripherals from the MCU cores? Then we have MCU plus SDK also, where there are reference display test examples which you can use it for reference and all these making display sharing or any other applications. So this is a software stack we have. So if you talk about display, we have a inbuilt SoC, we have the DSS IP, then we have a GPU hardware IP, then we have a video codec. And all these software components are like supported by standard Linux subsystem drivers. For example, this is DRM-based TI DSS driver, which is already upstream. Right now we are using RGX kernel module, which is also DRM-based. And very soon we are getting a true open source GPU driver also, which will be upstream. We have V4L2 based video codec driver. So these are all standard subsystems that we support. So you need not write anything specific to our codecs. You can use your generic V4L2 compliant or DRM compliant applications, and you can access all these hardware accelerators. For the middleware frameworks, we support GStreamer, which, as Shyam mentioned, it's a multimedia framework which is widely used and pretty standard. And we support Mesa umbrella of libraries also, which provide OpenGL implementation for 3D graphics acceleration, and which uses libgl ES, which is a graphics library for embedded systems. And to support this over the user space, we are using a Wayland as a windowing system, and Western is the reference protocol, or you can say server, which uses this Wayland protocol. And EGL is the glue, like it is a glue between your rendering API and the windowing system, which is Mesa based. So as you can see, there is little bit of blue here and here and here, right? So what does it mean? It means like there is some code which is not upstream yet, and very soon the GPU libraries will be supporting Gallium libraries, which will make the GPU fully open source from the middleware perspective also. Then you can directly use the upstream libraries that are provided. But even right now, from the user space perspective, you can use the platform-independent OpenGL libraries, APIs to program the GPU and have your hardware-accelerated rendering and rendering done. And suppose you are not interested in any windowing system, you just want to directly access the GPU in a full-screen mode. Then we provide EGLFS support also, which is EGL in full screen mode, which doesn't use any windowing system, and you can directly use like frame buffer based rendering to access the GPU and the peripherals. So on top of that, like you can develop HMI based application, which is the human machine interface applications, or for the medical appliances or the digital cluster examples. So let's go through the display features that we have. So here I'm taking example of the AM69 SoC. So as you can see, like it supports 3 industry standard interfaces. DisplayPort is there, DSI is there, DPI is there. You can go ultra wide 8K in DisplayPort, and it also supports state-of-art features such as daisy chaining, where you can have 4 back-to-back monitors connected to each other, each showing duplicated display output. Or you can use a multi-stream transport hub in case you are interested in having 4 independent streams and displaying it. And we have unique features here. We have 10-bit support, color processing is there, gamma correction is there. Then on top of that, as I said, we have safety features, like there's a display pipeline isolation, and there is a freeze frame detection. We'll see that in the further slide, what is the safety features, so I will just explain that. Software-wise, we support this in DRM, QNX, and FreeRTOS APIs. So as you see, like 6.9, we have the highest support of in terms of number of displays and resolutions. This is because nowadays in cars, you have like multiple display requirement with heads-up display, integrated cockpit, and the digital cluster and rear view entertainment. So this is a safety pipeline that I said. You have seen demos that my colleague had prepared. So let's say you want to have a display cluster with safety where the A core controls the graphics using the 3D graphics accelerator, and you want to control the safety related telltales from another core which is marked as safe. And so you can give one pipeline to the A core, another to the MCU, and you can have the screen rendering both together. So this is a hardware feature that we support. And if there is an error thing, like suppose in case you want to have some checks, like you want to have some region of interest where you want to make sure that it renders only an expected checksum of video, or you want to detect that when there is a freeze frame, then you want an error interrupt, then we support those also. Like you can get those interrupt service to another core which can do the error management and make corrective actions. So this is the demo my colleague prepared. You might already seen, like this one is GPU rendered, and this one is controlled by an DMR5 core. And now we crashed the Linux. You can see we have crashed the Linux. And you will see that the GPU part is freezed, but the safety telltales are still on. So this is the one POC of the safety feature we have. Coming to the codec, as you have seen in the previous slides, we support hardware video codec, which supports 8-bit format. We have 420 and 422 also there. We support up to 4K p60 equivalent load, and you can have multiple streams also, like you can do 32 streams parallel processing, and it can go as high as 8K to as low as 256 cross 128. And the beauty of this codec is like not just about the video coding capability this has, but it also has very good non-codec features like rotation and mirroring. As we have seen, like in camera mirror system, we want a mirrored output getting displayed or fed, right? So this support rotation and mirroring. There's a chroma format conversion also, because many times your camera supports some format and your codec supports another. And there is 3D noise reduction, like in night vision especially, there's a lot of white noise that needs to be corrected. So there is a 3D noise reduction there. And there's good latency tolerance, low power consumption. So this helps in real-time use cases and uses like doorbell security, where you want to record when somebody has come near your doors, and also it saves a lot of power. And we support also frame buffer compression, which is a lossless frame buffer compression that is used for doing intermediate processing, and this helps reduce the DDR bandwidth. And the software story is equally robust. We support standard V4L2 M2M framework. We support OpenMax in the QNX, and it has the low power support, software support also available, so it saves power also. So this is the one demo that is there, that is played from the SDK. You can see there's still some window that is present. So it's a Qt rendered GPU accelerated rendering using the hardware video codec. Here we are decoding a 1080p 60 stream kind of stuff. So it's pretty smooth. Coming to the GPU, we support BXS 464 GPU. So here 64 is the number of cores, and it supports 50 gigaflops with very good processing rate. And we support OpenGL ES2, Vulkan is also there. And as I said, like we are moving to upstream strategy, so very soon we will have all the middleware stuff also going to upstream with Gallium support. We support multiple operating systems like Linux, QNX, Android, and there are advanced features like you can have up to 8 virtual guests. There is frame buffer compression that is here. Safety is there. There is one innovative feature that is tile-based deferred rendering architecture. So as you know, like standard GPU pipeline, you have vertex shader, which transforms the matrices and does rotation and prepares your vertices that need to be rendered. Then there is primitive assembly where your vertices are converted into polygons, triangles. Then there is a rasterization where they get converted into pixels. Then the pixels are fed to fragment shader, which adds the texture and fills those pixels. And after all this, there is depth testing. Now in depth testing, what it does is like there are multiple planes of video that need to be rendered, right? So in depth testing, what it does is like it deletes the planes which are not going to be visible ultimately to the user, right? Because they are not needed. So this is a standard place of depth testing, but with this architecture, we are moving this depth testing at a initial stage. So we have vertex shader, then we have this tile-based deferred rendering architecture, which does the depth rasterization, depth testing together, and there at the starting place only, we eliminate all those planes which are anyway not going to be visible to the end user, right? So there's a lot of bandwidth saved there, DDR bandwidth saved there, and lots of good performance achieved there. And then we do all the fragment shading and all the other operations that are required for the rendering. So this is the GPU demo as from the SDK I'm running. So as you can see, there are level of tests. There is a 0 which is a pretty easy test. Then we go little higher. There's a more intensive playback here. And on the left side, you can see we have the benchmarking scores for the FPS and score. You have to run the video for almost like 1 minute and you will get a score. So this is the highest load, and you can see like the load is almost like full for GPU. And this is the default demo that we have for the motor control. Yeah, so if you have any questions, then please let me know.
You can raise your hand if you have any questions. Devash might look a little small, but he was flexing the technical muscle that TI has. So, yeah. One question then. Okay, yeah.
Has HDMI output?
Sorry, can you come again?
Does any of the processor from Sitara family has HDMI output?
Yeah, so as I said, DPI, right? So DPI, you can feed to HDMI. Like we have a bridge IC integrated in the board, each of the boards. In the demos also, all are HDMI monitors that we have connected. So we have a bridge IC that is there on board, which converts this DPI to HDMI on the fly, and you can use HDMI over there, like all the boards.
Without license, can we use that convert bridge?
Sorry?
Without HDMI license, can we use that HDMI bridge? I think no. I mean, user or developer has to go for license.
No, we are using the open source drivers for that IC. So it's already there in the Linux. It's GPL license, so you can.
Maybe for TI it is okay.
Yeah.
For others.
Others, I don't know.
Hello. On multiple displays, right? So is there, like you had some Tiltil and HMI together. I mean, no need to go to that. But do you have any POC tested, one with one display working with Qt HMI and any other with non-Qt HMI together?
One display with
Qt based HMI.
2D based HMI.
Qt
based HMI, okay.
And any other non-Qt based HMI?
Yeah, I think we can do that. So this is one example of display sharing, right?
Okay.
Where you have like same panel being accessed by different cores. But you can give like, we have multiple video ports. So you can like give one video port for one application and you can use another video port for another application. So we can do that, yeah. It's supported.
Okay. And another one, there are some Android-based targets also, right?
Yeah.
Whether any time Android and Qt coexistence did we try?
Android, I think it uses its Surface Flinger.
Correct, it's Surface Flinger.
Also,
similarly, one with one display with Android and another display is a Qt-based HMI.
So then,
did we try any time on that?
Then you have to use like one core running Android, another core running Qt. Now Qt is a Linux thing, so
Correct.
it also needs to run on the A core. So maybe you need to have some virtualization where you have like multiple A cores are possible. Like we have a quad core A53 or 8 cores E72, right? So
Okay.
some of the cores you use for Android maybe, and the other cores you use for that. So that's
Okay.
my
But what would be TI support in case if they go for that?
I don't know. We have to do POC and
Okay.
I have to check. But
Yes.
that's my thought. Like we have all these multiple cores of A cores, right? So we can isolate between multiple OSs.
Okay. We had a design query back at office, so I just asked for that.
Okay.
Ask the end application. So what's the
Yeah.
end application?
So what's
for
the
this?
end use case you have?
Display cluster only.
Display cluster, you want to use Android for IVI and
See, Android and Altia, we were able to do it.
okay.
But they wanted Android and Qt. which
Android?
we tried did not happen.
Okay, and why do you want Qt?
Their applications are already in the Qt. They wanted to use the same that way.
Okay, we'll take it off. Thanks.
All right. A big round of applause for Devarsh. Given us glimpse into the world of accelerators and software interfaces, showcasing how they empower us to build differentiated and UI-rich products. As we absorb this knowledge, let's appreciate the artistry involved in creating a visually captivating user experience. Thank you, Devarsh, for sharing your wealth of experience and knowledge with us today.